All right, welcome everybody. Good late morning, I guess. Hope everybody enjoyed your pizza. And if there's any left over, feel free to have some more before you leave. Welcome to the annual Computer Science Undergraduate Research Symposium. And we have a nice schedule for you today. Before we start that, I just want to show you a couple things here. There are a couple faculty who couldn't make it and wanted to talk a little bit to you. This first document is from Dr. Erin Walker, and she's actually looking for undergraduates for her lab. So if you are interested in that, her email is right there, eawalker@pitt.edu, eawalker@pitt.edu. So if you haven't had a chance to read that, we'll probably post it somewhere afterwards. But she wasn't able to talk, but she is interested in undergraduates for research. Second thing is not directly research, but it's another kind of a degree option. The Learning Sciences Transcript Distinction, sponsored through the LRDC, Learning Research Development Center. And some of our faculty are involved in that. And this is just a web page, so if you're interested in that, check that out. Again, it's not really research, but it's a addition you can get onto your degree. It's kind of a nice idea if you're interested in that side of computer science. Okay. With regard to today's actual talk, we have a nice program for you today. And our first speaker will be Dr. Akash Gautam. But I just wanted to say a couple things before that. So there's a lot of research going on in the computer science department. We're an active research department. And many of our faculty are engaged with undergraduate students. And as an undergraduate student, there's lots of ways you can utilize research either for or in addition to your degree requirements. So one probably common way is the capstone requirement CS 1950. So CS 1950 is a directed research course. You take that for 3 credits to satisfy your capstone graduation requirement. You need a faculty sponsor in order to do that. And so any of these talks today, if you talk to the faculty afterwards and are interested in pursuing research in that regard, you could potentially do a research project to satisfy your capstone requirement, which is really a nice thing. Even if you have another capstone, you might be doing an internship. There's no rule that you can't do more than one. So just keep that in mind. You have to have a capstone experience, but you're allowed to have more than one. So if you want to do an internship, you want to get some work experience, but you also want to do research, you most certainly can do both. Okay? If you are interested in doing research and you have another capstone, we also have a non-capstone research course. So you can actually take a research course that doesn't count for your capstone, but you can still do research for that. The requirements are a little bit less strict for that, but that's another option in case you are doing another capstone and you still want to do research for academics. Some of our faculty also may have some funding, and so it is possible that you could actually do research for money, for pay. That is something you'd have to talk to with the faculty member, but that's also another option. You can do research as a paid research assistant student. So that's something else to think about as well if you don't want to use it for your capstone. Okay? If you're interested in doing research and you're not sure how to pursue it, I'm happy to talk with any of you about kind of the overall process and how to pursue that. And obviously any of the faculty here, after seeing these talks today, if you want to talk to them directly, please do so. We encourage you to reach out and talk to them and ask questions. You're not going to know the answers unless you ask the questions. Okay? All right, so our first speaker is Dr. Akash Gautam, and he's going to talk about community-based technology design for social good. Yeah, you have to use the mic to record.
Oh, okay. All right.
There's no clip though, so you have to kind of
figure it out.
Just figure it out.
Yeah, it's weird, but yeah, we'll make it work.
Yeah.
All right, thanks, Don. All right. Oh, not this. This. All right. Hi, everyone. How are you all? So I'm going to talk about community-based technology for social good, which is part of my lab's work, and I'll introduce my lab in a while. But before that, I just want to introduce myself. I'm new to Pitt, so I'm an assistant professor with a dual appointment in the computer science department and ICDS. Previously, I was a faculty member at San Francisco State University. I completed my PhD a few years ago from Virginia Tech in human-computer interaction, which I'll talk about in a while. I have, other than like my academic work, have been moving around few countries. I'm from Nepal. I've studied in India, worked at PayPal as a software engineer, and then decided to move into academia, and since then have been associated with Virginia Tech, San Francisco State University, and now the University of Pittsburgh. I like to cook and eat, more preference towards the eating side than the cooking side, although I'm trying to watch that. And then I also like to watch football, what I call football, what many of you would call soccer. My research falls in this broader domain of human-computer interaction. Just by the show of hand, how many of you are familiar with human-computer interaction? Okay, quite a lot of you. Then I'll just briefly mention what HCI is. HCI is concerned with the design and use of computing technology. Now that's a very broad definition. Everything within computer science would be concerned with the design and use of computing technology. But the particular focus of HCI is around the human aspect of how do we approach people, who do we approach, what sort of methods do we use when talking to people, how do we listen to them rather than imposing our beliefs on them. Building on those initial findings, how do we design systems, and what we choose to design, what modalities and what type of interactions do we choose to design. How do we iterate during the development on those processes, and how do we involve people during those iterations? How can we evaluate our design systems, and what does those evaluation metric look like? And how do we maintain and sustain technology? The how questions behind all of these is what HCI is concerned with. And in all of this, of course, the research is important, but the human is important. Who are we designing it for? And that's the focus of my lab's work as well. Now, as you can guess, HCI is quite broad, and at Pitt, there are a range of HCI work that is being led by various faculty members in computer science, but also in the other departments within SCI. Our lab's flavor of HCI is community-based design work, focused on co-designing systems with people, with community members, with the goal of empowering the community members. So we work with marginalized and vulnerable populations in thinking about how can technology help empower the population. Now, in some cases, technology may not, and that's perfectly fine. But in those cases where technology can help, we engage with those in those contexts. So, in general, I have a belief around 3 pillars of doing research work. First is on the focus on methods. Methods means how do we reach out to people, how do we talk to people, and how do we design. And primarily my research work is around participatory design work. So we engage people right from the beginning and all throughout the design process. We try to build what we want to achieve into our process and pay attention to how we do things. Rather than the outcome, we focus on the process itself. And one of the things that we've been trying to do is look at what's already working in the community, what are the strengths or what are the assets already available to the community members, and then trying to amplify that through design. I don't see technology as the outcome. People and their values are what we care about, right? Technology becomes a means for that thing. So we understanding people's goals and their aspirations, their needs becomes primary in our work, and helping them overcome the limitations that they see for themselves is part of the empowerment work. We also think about what happens when we leave the project, like what happens to our technology, how does it sustain beyond that? That's another thing that we are concerned about, so we pay attention to those factors after our project ends. And if technology is not the means, then what is the goal here? The goal is relationship building. We want to build trust with community partners so that they can engage over a long time with us. Well beyond your undergraduate years, well beyond, hopefully even beyond, that's the hope, even beyond my tenure here, right? Partly building relationships requires attending to power differences and understanding who has power to shape the project in the way they want. Is it the researcher, is it the community partners, and how do we negotiate that? And in all of this, we want the community partners to gain something out of it. So we try to build in reciprocity through several slow steps. Some of the ongoing work at our lab, and you may have noticed I keep saying our lab and there's no name yet. You're welcome to suggest names if you want. Currently, we're thinking about STY, like as in a pig sty, which means society, technology, and you. But as you can imagine, like it's in a very, very nascent stage, so you can come in and shape the name of our labs, and that's the extent of which your influence can be, right? And some of the work that we've been doing is in supporting safety and empowerment of survivors of intimate partner violence. This work has been based in the Bay Area so far, where women who are either in abusive relationship and are contemplating leaving an abusive relationship, or who've just left an abusive relationship. We've been working with such group of people and the nonprofits that supports those women in thinking about how can we design technology to empower the women group. The other one, slightly in a different degree or angle, is to leverage some of these strengths people already have in facilitating multilingualism. So if you notice, like, people speak many languages other than English, but technology has been primarily in English. So how do we facilitate people to have more empowered use of technology by leveraging some of their existing language skills has been another project. One of my students here at Pitt is also looking at building on everyday practices to enable critical AI literacy, especially among adults, through collaboration with nonprofits in Pittsburgh. This is a project that has just started, so if AI and AI's application in society interests you, it may be something that we can talk about. And then finally, one of the projects that I want to engage a little deeper is on supporting people who've previously been incarcerated and are now trying to re-enter into society, and various measures to support them in their re-entry journey. So just a brief about this. This project began 2 years ago, and it's an ongoing project. It began with a collaboration with a nonprofit in San Francisco. Since then, it has expanded, and we're trying to expand here in Pittsburgh as well. It began with an initial interviews with people, formerly incarcerated individuals who I call returning community members, as well as staff members in the organization. And then those discussions involved 3 rounds of group discussions as well as multiple interviews to identify the problems. And some of the problems that we identified were around lack of digital literacy, lack of financial literacy, as well as challenges in finding jobs due to biases in hiring processes. And so that led us to design systems with around resources of around 6 major topics, including technology. This is too small for many of you in the back, I think. Technology in everyday life, technology for study and work, technology safety and privacy, financial well-being, also job application support, and accessing public resources beyond technology. We iterated on the tool and developed and deployed this. It's available to the nonprofit partner organizations and the people associated with that organization to use. We are currently evaluating how effective this tool is, and we plans to expand this further with various different various different technological features built into it. And then with that, I think I'm going to end. But if I want to invite you to think about working with us if you enjoy talking to people, and or you enjoy thinking about technology and the possibilities in solving social issues using technology. If you're interested in designing technologies such as wireframes and prototypes, or in building mobile or web apps, like, please come talk to me. Or if you want to kind of look at how to analyze qualitative data to see how research from user research ideas can lead to design innovations, these kind of work is valuable. In general, I think this is a pathway for people, especially if you're thinking about industry and thinking about UI UX career, or a full stack development, or even startup innovation. This kind of work can be valuable in learning some of the things that are essential for that. And my email is my first name at pitt.edu. That's akash@pitt.edu. So feel free to reach out after this session or through email. All right. I think I went a little overboard.
For each of the talks, we'll have just a couple minutes for quick questions. Anyone have a quick question for Dr. Akash?
Yes.
What is research?
Sorry?
What do we do to research if we apply to do that?
Sorry, come again?
Like, where do we do?
Where do we do the research? Right. So most of the research that you're going to do will be based in Pittsburgh. So we have collaborations with the Community Engagement Center in Hill District. We've been talking with a couple of nonprofits here in Oakland or in Sadie-Side. There's one project that we've been thinking about in Homewood. So mostly it will be in and around Pittsburgh, right? Because it is community-based, so it will be in the community. And the community for us is the city of Pittsburgh. Any other questions? No? Yeah, go ahead.
Is this what's the application for the incarcerated up in the community? Is that like only Pittsburgh based, or is that just like international?
That's a good question. So a lot of the problems are contextual, right? Like if you look at San Francisco, most of them aspire for a job in the tech industry, right? That's because that's the Bay Area, that's Silicon Valley, whatever you want to call it. There are lots of companies and there are lots of job opportunities around tech. So that's why a lot of focus was on tech learning there, even though it wasn't coding, but still like technical proficiency. Whereas if you look at the city of Pittsburgh, a lot of people who've been formerly incarcerated individuals, a lot of job possibilities are around construction. Pittsburgh is growing, the county is growing, there are a lot of construction jobs, and a lot of nonprofits have been putting kind of building a pathway towards construction. A lot of tech skills that we're talking about is not applicable in that case. So we'll have to change to fit that contextual reality. And that's part of the work. That's why we talk to people, right? Because the reality on the ground is much different than what we assume. And to kind of meet people where they are requires us to talk to people, right? And that's why it needs to change for Pittsburgh. And for international, I can't even imagine how many changes would be required. All right.
Thank you very much.
I see one.
Oh, wait, sorry.
Yeah.
Could you talk a little bit more about what you're doing currently with the multilingualism?
With the multilingualism, oh, that's a good question. We've been looking at older adults, especially those who speak Cantonese or Hindi at home and are uncomfortable with English. Like they do converse, but they often ask their children for help with technology, and their children are people who grew up here, who are not comfortable with their language in many cases. So we've been trying to understand the gaps in those language use to facilitate technology support. That's been the primary focus right now. Now, since then, there have been concerns that people have raised around cultural preservation, that their way of life that they were familiar with is not what their future generation is following, and they want some of the essence to be preserved through technology. And that has become a new means that has opened up for us to think about, one, technology literacy in the way they create those materials, but also to help with some cultural preservation very locally within a family or a small unit, not more broader group, but just for the family. So those are the two directions that we kind of forked around right now. All right? Yeah, thank you, everyone.
If any of you have any more questions, please contact Dr. Gao. He'd be happy to talk with you more.
Yeah.
Our next speaker is Dr. Lorraine Lee. And Dr. Lee will talk about probabilistic common sense knowledge in language.
Hi.
It's just for the recording.
Oh, okay, cool. Yeah. Hi, everyone. I'm a new assistant professor, just started this year as well at Pitt. Previously, I did my master at UMass, and then before joining Pitt, I spent 1 year at AI2 doing a postdoc. My main research interest lies at the intersection of NLP and machine learning, specifically probabilistic common sense knowledge. So there has been impressive progress. As we all know, ChatGPT and GPT-4 are all they're everywhere. So these interactions between us human and these large language models get really increasingly important. Then take this example. If we're using this Google Home and someone asks, I'm not able to find my phone. Where is, could you call me please? And then Google said, okay, now I will call you please. I will call you please from now on. So why this mistake happens is because large language model this model doesn't know place is not necessarily a person's name, and it's just simply a way that we say things. So the key aspect of a successfully deployed system, that means is handling this implicit information, that the information is not stated in this text, this kind of common sense knowledge. So this is where I argue machine need common sense. And then you might ask, doesn't this large language model, GPTN models already have common sense? Take this example. Which one is heavier, a croissant or strawberry in the same size as the croissant? And then GPT-3 said the croissant is heavier. And the similar responses come from all this very advanced large language models. They all think the croissant is heavier and gives you a lot of detailed reasons why croissant is heavier. So my answer is not really. Then what do I mean by common sense knowledge here? Take this example. They boil the water. We as humans shared a lot of knowledge about water, like water is liquid, water can be held in a container. So this is what I mean by common sense, is the implicit knowledge that is shared by all human beings about everyday matters. And then why is this common sense knowledge especially challenging for machine to have? One reason is because this knowledge we have for that one single sentence is massive. And then when we have multiple sentences, the knowledge is just simply too much. Not to mention the amount of text we're interacting with the machine every day. So it's a massive amount of knowledge. And also furthermore, in this kind of context, the important questions like, where do they boil the water and what kind of tools they use to boil the water? The answers for these questions include multiple correct answers. What's more important is the probability of each answer is different. Like we would more intuitively think the water could be more likely in a kettle than a beaker in a daily situation. But it's still possible the water is in a beaker. So common sense is probabilistic. It provides us with this probabilistic assumption rather than a definite answer when you are trying to answer this question. And then furthermore, if we change this context to and they boil the water and add the spaghetti, the answer changes even more. Now pot becomes more likely. So common sense is also contextual. And this follows back to my research interest. Is my research focused on designing models and evaluations for this massive common sense background knowledge. So I will first talk about this modeling part. I don't know, as we said, we need a probabilistic model, but in NLP, we typically just have a vector representation to represent each of those single word. It's not really probabilistic. How do you represent the probability of a mammal or a rabbit in this kind of representation? So it's not probabilistic. And if you go look further to this two concept, mammal is more general than rabbit. So this generality of the concept really doesn't captured by this vector representation as well. And furthermore, rabbit is mammal, but mammal is not rabbit. This is a really symmetric relationship if you're just using dot product or cosine similarity to compare the distances between the relationships between these two concepts. So vectors doesn't really do all of the things, and that's why we develop this box embeddings. So in this case, it generally represents the generality by the concept of how big your boxes are. And then the asymmetric between relationships can simply be converted into this intersection between boxes. And furthermore, we can use the size of the box embeddings represent the probability of that concept. Not only it could represent a single, like the concept like I mentioned before of those animal kind of simple concept we interacted with every day, it could also do this movie representation like we typically use in the recommendation system. This is the short training video of how these boxes get learned during the training process. So as we all can see, this Lord of the Rings movie representation all get closer as training goes, and then similar things happens with all the other movies. And this just mainly the modeling part approach, that's how we represent common sense knowledge. And these are just some represented like publications in this domain. And then the next research interest is on evaluation. How do we evaluate the probabilistic nature of common sense? And especially in this kind of prototypical situations, like what do people usually do before they leave the house for work? You can have all these different answers: take a shower, brush teeth, eat breakfast, all of these things. And then each of this answer have a different probability. Like more people say that they will take a shower, and less people will say they will say goodbye or pray or jog before they leave the house for work. So we're also working on proposing benchmarks to evaluate models' performance in this common sense domain probabilistically. And then furthermore, after we propose this benchmark, we say GPT-4, models like GPT-4 still suffers. So we're asking why this happens. And we claim that it's because, we hypothesize, not claim, it's because of the long tail problem, where the majority of the distributions lies on this common sense. And there are still some really, that things happens every day that is the kind of uncommon common sense. What do I mean by uncommon common sense? Here, give this context. Cameron tried sushi for the first time and really disliked it. The uncommon outcome is Cameron will want to stay and eat more sushi. Why would that happen? You guys probably will have some answer, but this is one of the answers our qual worker gave us. Because Cameron tried to avoid disappointing his partner who's excited about sharing. So we just propose this benchmark to evaluate the model's ability to generate this sort of explanations in these uncommon scenarios. And this is the evaluation part of my research. And furthermore, I have the limitation. Another big line is to study the limitation of large language models. And this is a simple multiplication task where it seems like it gives you a really reasonable answer, but that's not true, not the correct answer. What if you ask it to think step by step? It gives you something that looks really sensible, but still incorrect. So in this, along this line of research, there is like 2 represented papers along this line of research as well. And just in general, I'm interested in the modeling aspect, the evaluation aspect of common sense, and also study the limitation of large language models when it comes to knowledge representation or common sense representation. And if you're interested, you should just send me an email. I think it's right here. And if you're interested in like NLP, study the limitations of large language models or probabilistic modeling, or just like, even if you are just having any questions about doing research, send me an email. And thank you.
Time for just a couple quick questions. Anyone have any questions right now?
For your first part of your research with probabilistic modeling for common sense, what is the abstract space that you're actually like placing these boxes in, and what are the constraints of the size for that abstract space?
That's a great question. So the constraints of size, we don't really have a size. It's all in Euclidean space, right? So the size of the boxes depend on your training data, what kind of probability you gave the boxes for it to match. And then the application will apply box embeddings in not only common sense representation, not only the simple hierarchical relations between concepts, but also common sense knowledge graph, and also sentence relationships like entailment relationships, things like that. There are, all those different applications right there.
Thank you.
How are we going to exactly apply those modeling in stats? Are we going to just work on this ChatGPT language model, or if there's other platforms or forums we can check if the language modeling is going better and is working fine?
Yeah, there are many open source language models right there, right? There has been more and more and more that on a lot of the tasks they have on par performance with this OpenAI large models, where you could actually study the model the predicted probability, the logics, the weight of the model, and then do some more modifications instead of just calling OpenAI APIs. Yeah, go ahead.
How do you keep the efficiency of doing these operations on the boxes? Because the advantage of using vectors and vector spaces is because GPUs are really good at vector computation. So how do you, what's the trade-off in the, what is the good representation in memory of in boxes?
That's a good question. And I think in this box representation part, we applied this short, they're all kind of a shallow representation, meaning you don't need a lot of computation. You don't need to distribute them into 10, 8 GPUs for it to work. And that's actually, which is very efficient. But that's actually one of the disadvantages of boxes as well. How can you make it bigger? How can you make it a neural network that could work similarly to this large language models, to these transformers? That's another, that's a disadvantage of boxes, a drawback of it. But if we're just doing the simple calculation, it's very efficient. Yeah.
Thanks a lot, Dr. Lee. Our next speaker is Dr. Panos Chrysanthis, who will talk about graphs, data storage, and machine learning.
Okay. Here we are. Hello, everyone. So today I'm going to talk about graph storage and machine learning. So I will introduce my lab. I am co-directing the Advanced Data Management Technology Lab with Professor Labrinidis. As you see, the lab is 25 years old, so I will save you from telling you all my history in the last since the last century. Oh my God. I'm just going to say just briefly that the lab actually deals with the entire data life cycles from data acquisition, data stream processing, or processing of data on the fly, web data management, data dissemination. And just to give you a flavor of what we are doing, basically we are actually dealing with both algorithms, analysis of algorithms, development of prototypes, evaluation of systems, and so on. So we are basically engaging a lot of people, or undergraduate, master's students, PhDs in all aspects of this research. And again, these are over the years. In the past summer, I graduated my 20 and 21st PhD student, who Blackjack. And now I'm building my lab. And here is my current students. And these are the current students and their contributions. So we're looking into data KA operators, a new operator that replaces the delete through post-diction machine learning. We look into spatial temporal, mobile, and IoT. We have the Caprio system, and then we have the Retina for reproducibility. Brian just delivered this presentation in Germany, and he did an outstanding work, as the work that my other two students have done, Anna Baskin and Vasilis Saris. And now I'm going to talk a little bit about these two other contributions. But wait, why should I talk? The students are here. So I will pass that microphone to them to exactly tell you what they have done through the horse mouth. No, not horse mouth. Come, this is Anna Baskin.
All right, well, thank you very much. So I'm going to present some slides from a conference presentation I actually recently gave. I'm an undergraduate senior here. I graduate this semester. And my goal here is not just to give you a sense of the work the lab is doing, but also really make research seem a little bit more approachable, maybe. It's a really, down to the basics, it's a process of finding a problem and testing a solution. So what I was working on was data post-diction. And the idea for data post-diction is to reduce database storage costs by enabling the deletion of entire columns. So whereas prediction uses machine learning to estimate some future value, post-diction uses machine learning to estimate the past value of a field that's been deleted to free up space. So as an example, say you had a healthcare data set where you could use weight to predict height, AP high, and AP low, which are both blood pressure measures. That means that you could delete those extra columns and just save the machine learning models needed to recover them, which would allow you to see some huge storage savings. The problem we were looking at was how do we increase the accuracy of the recovered columns so that this is actually feasible in an industry environment. The solution we decided to test was creating a whole pipeline that adds clustering, outlier detection, and accuracy tuning. And so what I'm going to go through now is kind of a visualization of this pipeline. And this is using height to predict weight so that we can delete the weight column. And this is actually using a real-world healthcare data set, so I can show you kind of the actual accuracy and storage savings we saw. The first step is outlier detection, where you're going to move all the outliers into a separate outlier table where weight wouldn't be deleted. This, we would hypothesize, would increase the accuracy of the remaining recovered data because the machine learning models could be more accurate with the outliers removed. The second step is clustering, where the remaining data is clustered into different groups, and the machine learning model is going to be trained on each group, which should also increase the accuracy. And what we did find was that the recovered accuracy went from 18% to 47%. In this case, we defined recovered accuracy as the percentage of recovered values that were within a given error threshold. We set it as 5%. So in the recovered accuracy of 47% actually means that 47% of the recovered weight values were within 5% our error threshold of the original weight values. So the next problem you would say is if we want to deploy this to industry, especially with sensitive things like healthcare data, we probably want a much higher recovered accuracy. So how do we guarantee that recovered accuracy, or that those recovered values are going to be within our designated error threshold? That's where accuracy tuning, the last step in the pipeline, comes in. Now that you've trained your models, you can get the prediction error for all the weight values and simply remove all of those with a prediction error higher than your error threshold and move them onto the outlier table. So now you see recovered accuracy of 100% because you've guaranteed all of the recovered weight values are within 5% of the original. But you do have to be conscious here that there's a trade-off between increasing that recovered accuracy and decreasing your storage savings. So now you're saving a whole separate outlier table where weight is not being deleted. And with clustering, you're also saving multiple machine learning models, one for each cluster. So there's a trade-off there that you have to be conscious of. But now that you've created your outlier table and your clusters, you're able to completely delete the weight values. And so you're left with a recovery table that just contains height, a machine learning model for each cluster, and a separate outlier table. So from then you can see the percent outliers, you can calculate your storage savings, and with an error, if you implement the error threshold, you have a recovered accuracy of 100%. So that's the work we've done so far. We're still doing work developing the post-diction pipeline. We've got two goals right now. Our first is to add more outlier detection and clustering and machine learning algorithms so that the pipeline can choose whichever algorithm best fits the data that you input. The second part that's I think is really exciting is that was a really simplistic example of using height to predict weight. So ideally, we'd like to be able to delete many columns in the database. So we're looking into, say if you know that height can predict weight, weight can predict cholesterol and age, cholesterol can predict 3 other things. You could delete all those extra columns and recover them only storing weight or height. But so the idea there is how can we find that minimum subset of values or of fields that are needed to recover the other fields. So hopefully that gave you a good understanding of kind of this basic process of research and some of the work the lab is doing. I'm going to pass it over to Vasilis to talk about his project as well.
Awesome. Thank you. So my name is Vasilis Sadis. I am a PhD student here at the University of Pittsburgh. And I think my goal here is to kind of show you how research can lead into each other and give you an idea of like how my undergrad research sort of transitioned into where I am now. And so as some of you may have seen on sort of the first slides that Dr. Chrysanthis was presenting, I worked primarily on a project called Caprio. And so what Caprio is a indoor-outdoor sort of constraint-based navigation app. And so breaking that down a little bit, what constraint-based in this context means is that, a user can provide some outdoor exposure constraint, how long they want to spend outdoors at any given time, a total time limit, maybe they only want to walk, let's say 20 minutes in total, or maybe something like predicted congestion. And so this would help if maybe they have some weakened immune system and they want to minimize the amount of viral exposure they're likely to experience on their journey. We have a constraint for that as well. Or maybe they have mobility concerns, right? And so being able to control for that and make sure that any path recommended to them is sort of accommodating of those needs. These are all things you can set as the user. And so then the next piece of this is the indoor-outdoor paths. And so what that means is that, sort of very literally, the paths recommended to you are able to go in and out of the buildings, and that lets you get to your sort of destination faster. And my sort of main focus has been the pathfinding algorithms for Caprio. And so that started with Astro, and then I'll show you sort of the journey of my research with the extensions that we've made. But first, let's start with our indoor-outdoor graphs so you can actually get an idea of, how do we pathfind through them. And so if we're looking at an outdoor space, the way we're typically going to represent buildings are just going to be, vertices. And so that's no different here. We're going to have vertices represent these different buildings. And now we have to find some way of modeling our indoor spaces, right? So for this building, for example, Posvar, we're going to make, these vertices be all of the different entrances and exits for that building. And these are going to be our indoor vertices. And now, one of the constraints I was talking about was predicted congestion, right? And so this indoor graph actually has to be dynamic, right? It has to populate those indoor edges with the amount of congestion that the user would experience when they would arrive at that building. And so this indoor graph is actually, dynamically constructed during pathfinding. And this is how we model both indoor and outdoor spaces within the same graph structure. And one thing that's sort of interesting to note here is when we're looking at our edges between outdoor vertices, what we're actually looking at isn't edges between outdoor vertices, but edges between indoor vertices that are being used as the entrance and exits of those given buildings. And so that's the basic idea of the indoor-outdoor graph. And so now let's talk about sort of the pathfinding. And so when I first joined the lab, the pathfinding algorithm was Astro, and this was the only one we had. And you can think of this as just a basic A-star sort of application in indoor-outdoor graphs. And so what that means is that, its sole goal is finding the fastest way between point A and point B. And so it'll get to an outdoor vertex, it'll dynamically construct the graph, and then just find the fastest way through here that still matches our constraints. And this is the main idea behind Astro. And my first project when I joined the lab was, okay, well, if we recommend that Astro path to, let's say, 30 people, right, it's going to give the fastest path for all 30 of those people. And so, part of this is congestion and our predicted congestion. And that's based on a model of what we knew historically. But if we now put 30 new people into this space, our predicted congestion sort of no longer is going to be as helpful. And so our goal is to distribute the people that we're actually recommending paths to along maybe the top 3 or top K paths to our users. And the reason why they have to be sufficiently distinct paths are because if we, maybe the fastest 3 paths are all into the same building and, just exiting through different outdoor vertices or indoor vertices. Well, that's not all that different, right? We're still congesting that space. And so what we need to do is actually find these paths that are sufficiently distinct or different enough that they're going to populate different portions of our graph. And that was my first project, and that was my undergrad capstone. And now my master's capstone was Astro-C, a new pathfinding algorithm, sort of an extension of all of this work about now finding the least congested path. And so how do we now change our pathfinding algorithm that was based on time and the fastest way to get somewhere to now be based on these predicted congestion values? And a tough piece of this is, normally we can make our predictions based on time, right? The distance is never going to change between 2 points. But congestion is dynamically computed when we create these indoor graphs. And so that was a sort of the main challenge of that work. And now the next steps that, maybe you could be a part of are with creating and generating these new indoor-outdoor, randomly generated indoor-outdoor graphs, making this more usable to people. Making a whole indoor-outdoor graph representing maybe the entire campus is a really costly and time sort of costly thing, right? We have to map through all of our buildings and do all of our data collection for that. And so what our random graph generator allows us to do is actually generate these sort of realistic indoor-outdoor graph environments that we can now test our pathfinding algorithms on and sort of learn more about them. And we already have this realistic congestion prediction generator. It's EpicGen. It's part of our original Caprio paper. And so a goal for us is to be able to integrate this realistic real-world congestion with these randomly generated indoor-outdoor graphs. Thank you so much.
Thank you. Thank you both. Based on the fact that we have violated our time, the session chair said I'm not going to accept any questions. However, if you have any questions, please talk to me. And of course, please talk to my students. Thank you very much.
For the record, I didn't quite put it that way.
You know me, right? I have to make sure.
So our next speaker is Dr. Adam Lee, and he's going to talk about computer security and privacy.
Hey everybody, how's it going? Good. All right, good. I did not prepare slides because I'm just going to talk at you a little bit. So as Professor Ramirez said, my name's Adam Lee. I'm a professor in the department here since 2008. And my interests are in computer security and privacy, particularly from a data-oriented perspective, particularly from a somewhat collaborative perspective. So I've done projects with Dr. Chrysanthus. How many of you have had a class with Dr. Farnan? All right, Dr. Farnan was one of my PhD students. We worked with Professor Chrysanthus on the systems aspects of privacy and database systems. How many people have taken a class with Dr. Garrison? Also one of my former PhD students. He and I worked together on sort of the mathematical modeling and proving stuff about the security of systems. How many people know Dr. Farzan? No, she's in information science, or associate dean for DEI. She and I do some work together looking at sort of the human side of privacy and security. So understanding how people perceive systems to operate, how they model what's happening with their data, and how they decide whether or not they're comfortable with data collection. So we do some work looking at IoT-based sensors like connected cameras, voice assistants, and we've got a project that we call Tangible Privacy that looks at trying to build systems and sensors that by their very design convey what they're capable of collecting and what they're currently doing, right? So as an example, right, let's say you come into my office and close the door behind you, right? You sit down to have a conversation. You say, we've got 4 walls and a big thick door. I can talk freely, right? If I have an Amazon Echo on the desk, now all of a sudden you're not so sure, right? There's a microphone array in there and a pretty little LED that tells you whether or not the LEDs are on. And you don't know whether it's recording or where it's transmitting that data. On the other hand, if I could grab that device and sort of untwist the top, like the lid of a peanut butter jar, and put it down and disconnect the microphones from the computational elements, you'd feel pretty safe knowing that we can have a conversation that's not being recorded by that thing. So there's a lot of ways that design and interaction play their way into how we perceive how systems work. Of late, a lot of my work is joint with Professor Beal, who's in computer science and information culture and data stewardship. And we've got a couple of graduate students and undergraduates working in the space of sensing in collaborative and shared environments. So for those of you that were around last year, if you saw like black GPUs taped to the wall, those were ours, where we were looking at data collection and ways that we could capture and analyze video data in a way that preserves user privacy. So one of our graduate students may have interviewed some of you, interviewed some of our faculty and staff, and understood, what sort of information do people want to know about how data gets used in these sorts of environments? How do we collect that data? What are we comfortable sharing versus not sharing, right? And so what we found were that, we could come up with some visualizations that instead of showing the picture of me as a human, showed sort of a heat map of where I've been in the last couple of minutes, seconds, whatever. Instead of showing in detail the layout of this room, showed a wireframe of the room with where the furniture is. And people were comfortable with this because with that wireframe, I can see where there's a TV, where there's a whiteboard and all this sort of stuff, but I can't see what's written on that whiteboard, right? I can see that there's a desk and there are people sitting at it, but I can't see the books they're reading, right? I can see that there's a human standing there, but I can't see that they're wearing a Nirvana t-shirt or whatever. And so a lot of the analytics that people wanted out of the space, right? How occupied is this space now? Does this space have like the shared display that we need to do our work? Could still be done that way. So this is a long way of saying I'm interested in all things privacy and security. I kind of have a little bit of research ADHD. When I get stuck with the math, I like to do the stuff with people. When I don't want to talk to people, I like to do the stuff with the systems. And I enjoy collaboration. With that, I think I'm going to try to get us back on time a little bit. I was going to do a couple of tips and then questions, if that's all right. So I unfortunately had to miss Professor Ramirez's opener, so I apologize if I repeat anything. But I think research is great. It's my favorite part of being a faculty member. It's why I became a faculty member, to get to do things that no one else has done, right? So a lot of what you do in high school and as an undergrad is, you learn a lot. You're going to learn from what other people did. When you do research, you get to produce new knowledge, right? And that's kind of fun. And you get to ask interesting questions and you get to try to do new things. But it's not easy. It's an unstructured activity. You're going to be wrong a lot. You're going to, feel really, really unprepared most of the time. But your faculty mentor feels the same way, right? Going in, we're all going into something new. We're exploring a new area, and it's a growing experience. If you're interested in getting involved in research, I'm sure Professor Ramirez talked about the ways you can use research, right? For a capstone experience, for a 4-credit experience, for a 4-pay experience. There's lots of different ways to get involved. One of the frustrating things I think about research, both from a faculty perspective and I'm sure from a student perspective, is that finding opportunities isn't always straightforward. Like this event's great because faculty that are coming here are going to talk to you about things they're currently doing and places you might get involved. But one of the things that I tell students and the students that I work with even is that I don't have a list of projects that I want undergrads to do, right? It's sort of more of I've got a lot of projects that I'm doing with my graduate students. And if an undergrad's excited and motivated and wants to get involved, oftentimes we sort of spin off a side project and see where it goes. So my biggest piece of advice is if you're interested in research, and I'm guessing you are because you're here, is don't wait for a job posting. Is to go knock on doors, go to office hours and send emails, right? So people you've had a class with that you think is an interesting person and you might want to work with them, go talk to them. People read people's web pages, take a look at their papers, right? If the abstract looks interesting, ask to talk to them or their grad student and learn more about it. And these sorts of interactions will help open doors. And I know it's a scary experience to maybe go cold call a faculty member. But we have office hours for a reason. It's to talk to you guys. So do your homework, see figure out what your interests are, see who's working in that space, and go talk with them about it. Now, all of that I said about there not being job ads, Professor Littman asked me to make an announcement for her. She couldn't be here today. So for those of you who have not met her, she's one of our more senior faculty members that works in the natural language processing, machine learning, and AI space. And she wanted me to mention that she has an open REU posting, so that's a research experience for undergrads, looking for sort of a more senior undergrad student with some machine learning experience to contribute to a natural language processing project that she's got. So if that happens to be your particular cup of tea, send an email to Professor Littman. And with that, I'll take a question or two, I guess.
Is her email littman@cs.pitt?
littman@cs.pitt.edu, yeah. And mine is adamlee@pitt.edu. So my name at Pitt.
How much base experience would you say is necessary to get started in research, or specifically more projects?
That's a great question. So for those of you on the call or who couldn't hear, how much base experience is necessary to get involved in research? Gonna depend. I've had undergrad researchers who come in, extremely competent programmers and systems people to build a very specific thing that we need. I have worked with students from their first day on campus. So it sort of depends on the project, right? So I had one year I had an undergrad working with me in their first year, and I was interested in some of the permissions that apps were using in the Google App Store at that time, before it was Google Play even. This was a while ago. And so I had them, it's like, okay, well, you're new to all of this. You don't have a lot of sort of technical skills, but you can certainly browse the Google Store, look for apps that have location properties requested, and like, let's look at what they're doing with that data, right? Whereas, I've had more senior students who are, doing like kernel hacking. So it kind of depends on the project, depends on the professor. And this is, going to be part of that conversation you have as you get to know somebody. Great question. Anything else? All right, thank you.
Our next speaker is Dr. Adriana Kovashka, who will talk about weak multimodal supervision for object detection and persuasive media.
Do you want me to use John? Hello, everyone. So this title kind of tells you I don't know how to focus what I'm talking about in this particular talk. That's okay. So when I started out my research, I was interested in understanding things that computer vision hadn't tackled before, such as media. And some of you know about these projects. Specifically, I was looking at advertisements. And what's tricky about those is that they sometimes use very complex images, very complex rhetoric to make a point. When I started, there was no, language models, and AI were not as good as they are now, although Lorraine has convinced us that they're not very good still. So one thing that makes understanding them challenging, in addition to the complex rhetoric they use, is that there's not a lot of data for them. And the knowledge that they employ is kind of complex, requires a lot of effort to annotate. I'm not exactly going along with my slides here, but on the positive side, sometimes those media will have multiple channels through which you can understand the message. So there would be images and text, for example. However, the relation between those images and text is not always direct. And so I'm interested in learning from noisy data and transferring knowledge across different domains. As my title implies, I'm interested in both kind of niche applications such as persuasion and media understanding, as well as extremely mainstream things like object detection. But really all of the projects I have going on right now kind of came from this interest in understanding advertisements. That led to some interesting directions, such as kind of understanding that I've tried over time to make more aligned with more mainstream directions in computer vision, just for the sake of not having to just being able to leverage existing progress. But I'll talk about a few of these. So one is learning from language. When I started doing this, kind of vision language work was not very common. Now all of computer vision is more or less vision and language. Recognizing objects that a human will have little trouble recognizing as what they are, but that don't look very typical, such as recognizing animals in cartoons, say. That's another interesting direction. And both of these, reasoning, so being able to answer questions about the content you're seeing that may be very high level. All of those came from this interest in advertisements, but again, they've spun off into other directions as well. So one of the things that I'm known for that I don't do as much anymore because it's actually pretty hard is understanding advertisements. So let's make this interactive. Some of you may have seen this image, some of you not. So what does this ad mean if it's not too small? Yeah.
Burger King is so good that the McDonald's mascot has to come and get some.
Sure, right. And at the time that we started, and honestly still today, computer vision systems are good at understanding things at a literal level. So what's in the image, they can generate you a very good, these outputs are very, very old. But they can generate you a nice, even natural language description of the image. However, they miss really the point and the intent of the image. And this is so we have a data set with these, which if you're following what I'm saying, a data set that's annotated with these is a little bit in conflict with what I was saying about weak supervision. However, this, you can think of this as just for evaluation. And one annotation we might have is food at Burger King must taste really good since even the competitor's employee secretly buys it. And why is it secretly? Because of the trench coat, right? Okay. Some of you may be sick of this image if you've heard my talk multiple times. We did work on this before a vision language model called CLIP, before ChatGPT, and now we're coming back to this to see what these models know about these. So we haven't tested this specific image to see to what extent they can predict secretly, but we are exploring some cool directions. And in my experience, just like Lorraine's, it seems they have very good common sense, but not all the common sense that you need. Certainly, it's AI is a lot better than when I started this research. Some specific challenges more on the common sense end is there's some human associations that you kind of need to human associations that these ads play on that a computer vision model or whatever AI model needs to be able to follow. I'm gonna skip this one. There's objects, not all ads, but some have these atypical objects, like this deer made out of junk and this cow made out of fruit. Vision models have some trouble with with recognizing these atypical objects. So this spun off into a project on what's called domain adaptation and generalization, which is about being able to recognize objects with these atypical appearance. Something that we're not doing much with that someone could work on if they're interested in is being able to understand what are the implied physical processes that these ads rely on, such as the melting earth and what this means. So again, so we train on this data set, but you can think of it as a evaluation setting. We have these ads with a whole bunch of annotations. The one that we've worked the most with are these action reason statements. And I'll show you an example of what this is. Kind of don't worry about reading the slide. So an action reason statement might be, I should drink Evian because it helps you recover based on this ad. So, what the rhetoric of this ad is basically. And we want to be able to predict based on the ad, a correct statement. So I'm not even necessarily going to talk about this. Something that I was interested in, so we have a variety of methods that try to do this task. Give it an image, predict what is the right description of it, specifically what you should do based on the ad and why you should do it. So I should buy Chanel because I'll be fashionable, or I should recycle because it will ultimately affect our environment. Again, at the time that we were doing this, there were not these foundation models that are supposed to have massive common sense. Yet we still thought, it doesn't make sense that we should even try to learn all the information you need to be able to do this task just on our ads data set. So transfer learning is a well-known trick. Specifically here, what we wanted to learn, what we wanted to transfer from were just general purpose, not ad specific knowledge bases. And it turns out working with knowledge bases is really tricky because in our case, what we found out is that there's a way for methods, which this is not quite clear in my ad, in my slides. Turns out that there's a way for machine learning algorithms to cheat. It's all up to how you set up the task. They'll do the simplest thing possible, and sometimes you think that this requires them to reason, but it doesn't. There's much simpler ways they can do this. And on our ads data set, and actually on other data sets as well, that we've done some work on that, it turned out that here you honestly don't need knowledge from a knowledge base to do the task. And so we ended up figuring out a way to make the task harder at training time, not at test time, just so that the model is forced to work harder. And it ended up, meaning that we use the knowledge base better, ultimately do a little better. But what this figure is showing you is in the middle column is a graph that basically shows you what information from the image or from the caption, it's not very readable at all, is being used to do the task, however we set up the task. On the right, these orange things are information from the knowledge base, and basically what you see is that we are using more information if we do our trick at training time, which is called masking. But then we did some work, again, going to something a little more mainstream as in other data sets beyond our ADIS data set. We did some work, if you look at the top left, because there's a lot on this image, on the top left, we basically show that the way some other data sets are set up is a multiple choice task where your algorithm is supposed to answer a question about an image. There's actually lots of ways for the method to cheat, such as just by doing essentially basic string matching rather than doing any sort of reasoning. Then we looked into doing reasoning in a domain robust way where you maybe train on one data set and are expected to do well on another. Here, this is visual question answering, and we're showing roughly a fixed setting like a dining table, but different data sets will have different visual appearance, questions will have different information need, and we just explore different ways to be able to be robust to these changes, such as the knowledge you acquire is somewhat general. Gonna skip this very much. So we also looked at news articles and the relationship between the image and the captions, or the images and the articles is fairly complex there. So we looked at ways to be able to retrieve across the modalities while capturing kind of this complexities and the fact that there's like figurative uses, that the same concept can be illustrated in lots of different ways. I'm gonna skip this because I want to stick to the 10 minutes. Basically, this is about learning to recognize objects from supervision that your method gets from noisy web data. And something that I've started working at more recently, so this was a paper on being able to recognize objects despite the modalities being different. Say, you have photorealistic data, so you have photos, cartoons, whatever this is, paintings, and you want to be able to recognize dogs in sketches. So you can't really tell what the method is here. We were trying to capture a shape in this particular work, but something that's actually similar in spirit, but has a different sort of practicality to it that we've started working on recently, and that I have some funding for, is to be able to recognize objects across different countries, because it turns out, so here we have cleaning equipment, which you can say is a broad category, but also things like plates, beds, stoves look very different across different countries. And there's been a small amount of work on this, but what we're interested in is can you use the essentially common sense from large language models to be able to bridge these gaps. The language that describes these images will also be different in different languages. Some objects tend to get mentioned in captions more than others. Be happy to talk to people about this offline, since it may not have made too much sense. And one thing that's part of this project also is being able to recognize rare objects that are specific to given countries, even though we may have very little data from these. So with that, I hopefully have 1 minute for questions. Thank you. Yeah. Yeah.
Can you explain more about how you define noisy data?
So we don't try to find noisy data sets, but the point here is nowadays people train on to recognize, say, plates from just content people have uploaded to the web with some sort of caption, but the caption might mention a lot of extraneous concepts that are not in the image, and so your model, if it's assuming that the caption exactly describes the objects in the image, will be confused. Similarly, not everything in the image will be described, so you have false. If you were to extract labels or supervision for your image from text that it appears with, you'll have both false positives and false negatives. So that's kind of what we mean by noise. We don't try to find noisy data sets. We try to just clean up existing. The point is that the data you find on the web will be noisy for the purposes that you're trying to use it for. And so we try to essentially find patterns in that noise as a way to clean up the noise, if that made any sense. Yeah?
Can we make well-known advertisement like general knowledge? Can we infer that from our data set in which red is used in advertisements because it is correlated with anger or some sort of like emotion. So this is like well known in the advertisement media, but can like AI models infer that?
Yeah, I mean, so there's different ways to understand emotion. There's emotions on people's faces. There's also implied emotion. So if you can create an image that will make somebody angry, right? And there's some data sets that look at that. If I remember correctly, it was still, whatever existing methods were there for this, they were still not enough for like ads in particular. But definitely there's, we should not be reinventing everything in this, there's lots of things that are captured by other data sets that would also be useful for ads. I'm probably out of time, yes? Yes, okay, thank you. I'm happy to talk offline, send me an email.
Our final speaker is Dr. Alex Labrinidis, who will talk about data management and data science for the common good.
All right. I guess I need to do this. All right, can you hear me? I guess I carry my voice anyway. So I'm very glad to be here. I'm the last, so I'm going to try to keep it short and sweet. And my name is Alex Labrinidis. With Dr. Panos Chrysanthis, we co-direct the Advanced Data Management Technologies Lab. And I'm going to briefly mention two recent projects that we have. One is still going, one is kind of ended, and some other ideas about future projects. So the first is this Pitmar Smart Living project that started pre-pandemic. And the idea there is you're waiting on your bus. You are given a warning that the bus is coming in 2 minutes. You're waiting and the bus is full. And then your plans have to change and, or you're thinking, should I squeeze in and so forth. So what we were looking into is how to, first of all, figure it out when the bus will be full, so people know ahead of time. The next one is if the bus is full, try to give incentives for people to do the right thing. And the incentive could be, you know what, if you take the bus that's coming after this, so 20 minutes later, we'll give you a coupon to go get cheaper coffee around the corner. And then another idea would be to, for example, suggest an alternate route that would take a bike for where you're going, as opposed to you just taking the bus for the whole way. So that was the original proposal. As I said, pre-pandemic, it requires collecting information from many sources, aligning incentives from local businesses who are going to do the advertising for people and give the coupons for people to come in, what travelers want, which is not going a full bus, and so forth. Then the pandemic hit, and a lot of these things either were no longer important because nobody would want to get in a full bus if they could avoid it, or we couldn't measure them because things got delayed. But we were able to do a lot of good stuff with this. It's just you don't have an app on your phones doing this right now, and that was because of the pandemic. So a lot of this were projects with undergraduate students. Some of the projects involve data modeling and predictive models. And for that, we had to deal with dirty data. So this is the yellow parts here are one particular bus route. 61C, I think. And then the red is bus stops, real data about buses stopping for 61D that their algorithm couldn't match them to a bus stop. All right. And then, some of these are close. So that means, there was a little bit off and it was not, a big deal. But some are way off. And when we showed this to the Port Authority folks, Pittsburgh Regional Transit, I guess now, they said, oh yeah, this is a completely different route. Someone forgot to put in the key code right, and that's why it's labeled as 61C, although I don't remember the number of it. If you zoom in more, you see there are some on the rivers, and this has not happened, because if it did, it would be in the news. You saw the sinkhole incident, but not anything in the rivers. So this is also another instance of dirty data that we will have to deal with in this project.
one thing that we did manage to do very successfully is put this display. So how many of you noticed there is one like that at the entrance of our building? Not that many. Next time you know that there is one there. And it has 4 bus stops around the area here. And one other cool thing that happened, we cannot take credit for it, is the Port Authority did announce, made available through their data API, their capacity in the buses. So this is live data given from the Port Authority that we're the only bus information provider that shows them. But you see what it is right now. If it's in a couple of minutes from now, that's accurate. If it's 35 minutes from now, maybe a lot of people this could go to green or red. Obviously, that's not a guarantee. All right. So that's happened. We still have some. We still maintain the screens. There's, in addition to one downstairs, we have 2 at City Hall. We have at the library. We have a few screens like that we're maintaining. We have a new project that we're adding some other capability. Next I want to talk about another new collaboration that again is for, we're using data for the common good. And that is together with the Center for Cardiac Arrest Survival. Any of you have heard this before? That's okay. All right, one person. So this is in Pitt's Department of Emergency Medicine. What they're doing is they're coordinating this pulse point app. This is an app that people that know CPR can put on their phones. And the way it works is if someone calls 911 with reporting that someone stopped breathing, that gets flagged. They get it, and then everybody that's marked to be a volunteer through that app gets a notification if it's within walking distance close to where they are right now. So let's say you're at the park, you're eating something, and then you get a notification that someone in the park, like a few feet away from you, is having needs CPR. Assuming you are trained, the idea is that you can take that and go there and hopefully make it before the ambulances show up. And the reason that this is important, every minute that passes after someone stops breathing reduces by 10% their chance of survival. So timing is absolutely critical. All right, where do we come in? We didn't build any of that. That exists. They're the ones that coordinating it a little bit, but that generates a lot of data. And normally they have something like this, so you can look at individual ones, but that was not enough for them to do their analysis. So over the summer, one undergraduate student from computer science worked together with me, and he built, I just gave direction obviously, a map-based interface for all these kinds of data that zooms in, zooms out. You can see these are incidents. When you zoom in or out, we change, we summarize and create clusters as opposed to having individual dots. And there's also filtering conditions. So this is all nice stuff with JavaScript. So you filter, then some of those dots disappear and all that kind of stuff. So this is one example project. There are a few more in the works with them, but that's something just to give you an idea of the types of things that we've done already. I promise to keep it quick, short and sweet. So this is, in general, the types of things we're looking at. So we like to build systems, and that means, at least the team is going to do full stack web development. Maybe your individual expertise is not complete full stack, but some part of this. But these are the type of stuff that we're working on. The type of expertise that's useful for the type of stuff we're working on. We do have, the need for attention to detail. You saw there's a lot of stuff going on here. To make it look half as good, you really need to, know what you're doing. And these are big projects. Usually you're going to be part of a team. And oftentimes you may be talking to non-computer scientists. So this is another type of skill that you need to be ready to explain or understand things that come from non-computer scientists. So this is the dashboard that I showed you, an example. We're also working on, things with chatbots like everybody else in the world, and updates to the digital signage. And, there are other projects that come up throughout, and this is not just the only ones. Usually these are either as a internship, which is paid, but more often these are in the form of a research capstone, and that's something that I routinely do a few every semester. My web page is this. It is up to date. It has my office hours, contact, everything. This website is still there. It's a little bit not very well up to date, but it has a few more things for you to get more details. Another thing to mention, a good way. So if you are remotely interested, please send me email. Usually what I will ask is, can you share with me your resume and your transcript so I see the type of background you have to see if there's going to be a fit. Another very good way to do a research capstone with me is take the class that I'm teaching, the Intro to Data Science, do well in that class, and then usually I pick a few students from that class every semester. The class is taught now. I don't see any faces from the class, but maybe one or two. Okay, sorry. All right, at least a couple, sorry. I'm also going to teach it in the spring as well, both sections. And so let me stop now, give a chance for a question or two if there's time. I'll leave this. Anybody else wants to follow up, more than happy to talk, start the discussion via email and in person. So let me stop here, try to be super brief and quick. Time for questions if you have any. Okay, I don't see any questions. So going once, going twice. All right, we are well over time. So I am available via email to follow-up discussions. Or in class, either this or next term. Thank you.
Thank you. Thanks everyone for coming. Just a couple quick reminders. If you have questions about anything with any of the speakers, feel free to contact them directly. If you need some information about contact information, let me know and I can put you in touch with them. As you saw, they're recording this. We're probably going to be posting that link somewhere. So if you want to view it again later, you certainly will be able to do that. And finally, there is a little bit more pizza and drinks and a lot of salad back there. So please help yourselves. Don't leave without taking some extra food. Have a nice weekend.
Thank you. Thank you.